morning to all. I am Dr.S.Kalaiselvi, Assistant Professor of Mathematics, Standard 5 of Rajarathinam College for Women, Sivagas. Today, in this video lecture, we are going to see about elementary matrix transformations. Already we knew about the definition of a matrix and the type of matrix and how to find the inverse of matrix. In this session, we are going to see about the elementary transformations. These elementary transformations are very useful to find inverse and also the solution for the system of equations. First, we see about the definition of a matrix. The matrix is nothing but a rectangular arrangement. It is in the form of row and columns. It can contain m rows and n columns in general. The matrix can be any type of matrix, that is square matrix or column matrix, and it may be a null matrix, then identity matrix. These are all the types of matrix. If a matrix contains the same rows and columns, then it called as the square matrix. For example, the matrix contains 2 rows and 2 columns, then it is a 2 cross 2 square matrix. Suppose a matrix contains 2 rows and 3 columns, then it is a rectangular matrix. In these matrices, we can form the elementary transformations. The elementary transformations of a matrix are important. It is used to find equivalent matrices and also to find the inverse of a matrix. Elementary transformations is playing with the rows and columns of a matrix. Now, let us learn how to perform the transformation of matrices with rows and columns. This matrix is a m cross n general matrix. First element is called as A11, that is first row, first column. Like in that way, we can call the second row first column means A21. What are all the elementary transformations followed by the operations? First, rule 1, interchange of 2 rows or 2 columns. Then the second rule is multiplication of each element of a row or a column by a non-zero number k. Then the third rule is addition of k times the elements of a row to a column or a row to the corresponding elements of another row or a column. Then first we are going to see an example based on the rule 1. Rule 1 is any 2 rows are interchangeable. That is, in this example, the matrix A contains 3 rows and 2 columns. We are going to perform a row operation, that is, we can change any 2 rows. That is, we are going to interchange the first row with the third row. So, we can obtain the matrix B as the given matrix A contains first row elements are 1 and 23 and the third row minus 13, 7. If we are applying the rule 1, that is, we are going to apply the rule as interchange the row R1 to the row R3. That is, first row is interchanged as third row. So, we can obtain the matrix B as first row contains the elements minus 13 and 7. There is no change in row 2. Second row contains the same elements as in the matrix A, that is minus 9, 5. Then the third row is changed as first row. 1 and 23 are the elements in the second matrix B. That is, we are applying the row operation rule 1, that is any 2 rows are interchangeable, or we can say that we can swap any 2 rows, that is interchanging 2 rows, that is Ri is interchanged into Rj. In this example, we are just changing R1 into R3. Then in rule 2, all elements of any row can be multiplied by any non-zero number. That is, the multiplication of ith row to any non-zero number k. That is, in this example, we are going to multiply the second row with the number k equal to 2. That is, the second row is going to be changed as 2 into R2. Here k is the number 2 and we are going to multiply this 2 with the elements in the second row. First, we are taking one matrix A that contains 3 rows and 3 columns. In this, we have to note down that the second row elements are 3, 5 and 21. Here we are applying the second rule, that is, the elements of any row can be multiplied by any non-zero number. Here we are multiplying the number 2 with the second row. Therefore, we can obtain the matrix B as in second row there is no change in first row and second row in our obtained matrix B. That is, B contains first row same as the matrix A. In second row, the elements are 3, 5, 21. So, we are going to multiply the element 2 with these 3 elements in the second row. The first element is 3. So, 3 into 2, 6. Then, second element is 5. So, we have to multiply by 2. So, we obtain 10. Then, third element in the second row is 21. Therefore, 21 into 2, we get 42. Then the third row is, there is no change in third row. So, the same elements 2, 1, 9 also appeared in the second matrix B. There is no alteration in first row and second row. This is the second rule of elementary transformations. Then the third rule is adding a multiply of one row to another. Here we are taking the second row plus third row. Here we are having the example matrix as P. We are naming the matrix as P. Here we can name the matrix in any 26 alphabets. So, we can give any letter for the matrix for a notation. Here we are giving the name for the matrix as P. P contains 3 cross 3, that is 3 rows and 3 columns. So, the matrix of order 3 cross 3. In this, we are applying the rule 3, that is, we are going to add second row and third row, and then we are going to keep the answer in the second row. Therefore, we are applying the rule as R2 implies R2 plus R3. So, there is no change in first row and third row. Is it? Okay. Then first we are going to write down the changed matrix. So, we have to give one name as Q. Q equal to first row is 1, 5, 4. Then in the second row we are going to apply the third rule. Therefore, here we are going to add second row and third row, and we have to substitute the answers in second row. Therefore, we have to note down the matrix P. In matrix P, second row first element is 5, then third row first element is 4. So, we have to add these two elements and keep the element in second row first place, that is 5 plus 4 equal to 9. Then in the same way, second row second place, that is second row second column A 2 2, that is 2 plus 5 will change as 7. Then for the second row third column, that is A 2 3, here we have to add 5 plus 3, So, the element is 8. Then the third row there is no change, so we can keep it as 4, 5, 3. So, we have obtained the matrix as Q equal to first row contains 1, 5, 4, then second row contains 9, 7, 8, then the third row contains 4, 5, 3. These are all the 3 rules for the elementary transformations. In these 3 rules, we are applying these rules for row only. We can also apply the same rules for the column also. So, we can name the transformation as column transformation. In column transformation also, we can apply the rule 1 as any 2 columns are interchangeable. Then the rule 2 as any 2 row can be any 2 column, that is all the elements of any column can be multiplied by any non-zero number. Then we can multiply the same non-zero number to any column. Then in third rule also we can add and 2 columns, that is C1 implies C1 plus 3 C3. These are all the column operations. First rule 1, any column are interchangeable. Here we are applying the first rule to any 2 columns. That is, here we are having 1, 23, then 9, 5 and 13, 7. Here we can interchange any 2 columns. Here we change the column as first column into second and the second column into first. In the same way, we can apply the rule 2. Here also we can multiply any non-zero number to any column and we can change the column as we can multiply by the non-zero number. Then in rule 3 also we are applying the row transformation as in the same way to columns also. Here we are applying the rule as C1 is going to be changed C1 plus 3 C3. In the first column we are having the 3 elements. We are going to apply the same rule, that is in first column we are having 4, 1, 2. So, here the rule is C1 is plus 3 into C3. Here we are adding and then multiplying a non-zero number. So, here we are applying the rule 2 and rule 3. First we have to multiply 3 with the column 3. So, we get 3, 3 and 6 and then we have to add the 3 elements with the first column. So, we get first row, first column, first element 4 plus 3, 7. Then second one is 1 plus 3, 4. Then third one is 2 plus 6, 8. So, we obtained the transformed matrix as B 7, 4, 8 in column wise. Then second column 10 minus 13, 5. Third column contains 1, 1, 2. Then what are all the applications of elementary transformations? First, we can apply these elementary transformations in the set of systems of non-linear and linear equations also. To solve the system of 3 equations or 2 equations or more number of equations, we can use these elementary transformations and then we can find the solution for the given system of equations. And then second one is finding the inverses of matrices. For finding the inverse of a given matrix, we can use these row transformation and column transformations also. Then third one is transforming matrices to row echelon form and reduced row echelon form. This is the example for row echelon and reduced row echelon. In the row echelon form, every matrix can be put in row echelon form by applying a sequence of elementary operations. The term echelon comes from the French word echelon, which means the level or step of the ladder, and it refers to the fact that the non-zero entries of the matrix in row echelon form look like an inverted staircase. That is, the last row, that is in the below the principal diagonal, all the elements are becoming 0. Any row consisting entirely of 0 occurs at the bottom of the matrix. Here also we are applying the rules of elementary transformations, that is interchange of any two rows and adding the two rows together and multiply one row by a non-zero constant. How can we apply the three types of elementary transformations? It can be either be of rows or by columns, but we cannot operate both simultaneously. If we using the row operation, then we have to apply the same row operations only, and then if we are starting from the column, then we have to apply the column operations only. This is an example to convert the matrix into row echelon form. Here also we are applying the same rules either by row or column, and then we are going to reduce the matrix into row echelon form. Then these are all the examples. These are all the examples for converting the row echelon form and reduced row echelon form, or finding the inverse row echelon form or reduced row echelon form to find the inverse in row transformation. For using or for finding the row inverse for a matrix, we can use the formula to find the inverse of a matrix, that is A inverse equal to 1 by determinant of A into adjoint of A, that is 1 by to find the inverse of a matrix. For that formula, we have to use the determinant value, it should not be equal to 0, then only we are able to find the inverse. But in this transformations, using elementary transformation to find the inverse of a matrix, we are not able to find the determinant value of the matrix. We are just using the elementary transformations. Then what are all the importance of elementary transformations? The elementary transformations are connected or found to matrix multiplication and efficient solution of the network transformations, and to find the transformation for the solution of a system of linear equations. And also there is one point, that is the elementary matrix should be a square matrix. Any elementary matrix can be a square matrix. The matrix differs from the identity matrix by one elementary row operation is called an elementary matrix. A sequence of elementary operations may reduce any matrix to a uniquely reduced echelon form. Simple row operations do not affect the solution of system of any linear system. So, as a result, the solution of a system is the same as the solution of a system whose augmented matrix is in reduced echelon form. So, why do we require basic row operations? The fundamental transformation of matrix is very critical. So, it may locate analogous matrices and the inverse of a matrix. So, we are using here the elementary operations and row operations to find the inverse or a solution of a system of a matrix. Here we are using the three basic elementary operations of a matrix: interchange of any two rows or two columns, multiplication of row or column by a non-zero number, and then multiplication of row or column by a non-zero number and add the result to other row or column. The transformation matrix transforms a vector into another vector, which can be understood geometrically in a two-dimensional or three-dimensional space. The frequently used transformations are stretching, squeezing, rotation, reflection, and orthogonal projection. And then if the non-zero matrix is an elementary matrix, because the zero matrix can be obtained by multiplying each of the rows of the identity matrix by 0. And elementary matrices are always invertible. because they are obtained from the identity matrix through a single elementary row operation, such as interchanging two rows, multiplying a row by a non-zero scalar, or adding a multiple of one row to another. The rank of a matrix does not change by the elementary transformation. So, here we can conclude that the rank by changing the matrix into echelon form. In the echelon form, the rank of a matrix is the number of non-zero rows of the matrix. If the rank of a matrix is 0, if the matrix is null, no, the elementary transformation of the matrix does not affect the solution of the system of linear equations. So, thank you all. In this session, you are learn about the elementary transformations of a matrix. I hope that this lecture will be useful for you. Thank you.